Welcome to another tutor short provided by the Educational Support Services Department of Lehigh-Carbon Community College, which is in Schnecksville, Pennsylvania, just outside of Allentown. These videos review key learnings from our science courses here at LTRI-C, and please remember that the Educational Support Services Department does provide walk-in tutoring. This video will review constant acceleration in one dimension. Now this is applicable when the magnitude of acceleration is constant and the direction is in a straight line. This is often called uniformly accelerated motion. And it means that the velocity is changing in a linear fashion. When you work a problem with this, as you will with all physics problems, you will set up a coordinate system. And for this situation, you would have an initial conditions of distance, time, and velocity, and a final conditions for your distance, time, and velocity. And over this period of time, you have a constant acceleration occurring. And while you're in that condition, then any of these equations is applicable, and you will use the equation that makes most sense and gives you the answer in the quickest way with the least amount of math. But you get to choose whichever equation you want to use. So let's take just a simple little setup here. Let's assume we have a situation like this. Here's our direction of travel, and we'll put our velocity here as a y-axis. So we're going to have a car that starts at 30 miles per hour and going to speed up to 60 miles per hour. So at some point here, we have t0, x0, and v0. And this, at that point, is where the car is going to accelerate until it reaches the 60 miles per hour, and then it stays constant after that. So at this point here, we have t, x, and v. Now normally you will set t0 to 0. In this case, let's say we know our initial position, say it's at 10 miles. We know our velocity initially was 30 miles per hour. We know our final velocity is 60 miles per hour. Let's say that in this time period we got up to 40 miles away. And let's say we're looking for our t. See how long it took us to accelerate from 30 to 60 miles per hour across a distance from 10 miles to 40 miles, or an overall change in distance of 30 miles. Now we also don't know, in this case, we also don't know the acceleration, so we're going to look for that also. So we're looking for time and we're looking for acceleration, and we know the other variables. So we can go back now up here, and a nice way to start is if we go over here, we know our initial and final velocity, so we can calculate our average velocity. And once we know our average velocity, we can use this equation, because we know x and x0, we can solve for t. So using this combination, we now know our time t. Now to find our acceleration, this is a pretty simple looking equation. We do know v and v0. We now know t, so we can solve for a using this equation. But we also know these variables, all of them except for a, so we could have picked that equation, done a little bit more math, it's a little more complicated, but we could have found our acceleration. We could even have used this equation and gotten our acceleration from there. Because of the square function, it's a little bit trickier, but we could have used any of those in order to find acceleration. So I wanted to make the point here that any of these equations are applicable while we are dealing, if you remember, in this range of this problem. That's when we're doing constant acceleration in one direction. these equations do not directly apply in these other areas. They would basically simplify because A is now 0. There is no acceleration. But the equations I show you here with a constant acceleration apply when we're having that constant acceleration. Let's now deal with a problem of constant acceleration in the vertical direction. The equations are going to stay the same. We're still only moving along one axis, only now it's the y-axis instead of the x. So the equations I showed on the page before, you can still use them, only now you're going to substitute y for the x in those equations. But also what is different about vertical acceleration problems is we do know our acceleration because we're here on the Earth. If the problem you're dealing with is on the Earth, we know the acceleration of gravity is going to be directed in the y direction. And so we know our acceleration, that's the force of gravity of 9.8 meters per second squared. And if we set up our axis as I have shown here on the right, where a positive y is the upward direction, if, as I show here, y is in upwards, therefore our g is going to be negative. So for a in the equation, you would substitute a minus 9.8 meters per second squared because it's acting in the opposite of a positive y direction. It's acting in the negative y direction. Now, typically in a problem involving this, which is when a typical kind of problem would be someone tossing a ball up in the air. And so you have a ball over here, and you toss it in the air. Now, even though they may show it as a loop, they'll probably mention in the problem that they want you to deal with this as a one-dimension problem. So by using the equations that I showed in the previous page, you're essentially just saying it goes straight up and straight down. And so they may show you with a little bit of an x direction here. You're going to ignore that, and the equations are really just for straight up and straight down. If you were to involve an x direction, now you're talking projectile motion. It's in two directions, and it's a different type of problem. So we're going to use the equations I showed you. There are some unique situations, sort of what I call shortcuts, that can get you quickly to an answer. One thing to remember that if you, in this case, we're saying we're taking a ball and tossing it in the air, at the peak here is where the ball stops moving upward and it's just going to start moving downward. So we know up here your velocity in the y direction is 0. So there is a split second when the ball has stopped moving. But remember, acceleration is not 0 at that point. Your acceleration is still minus g. Gravity is still applying its force on that ball, even though it's not moving. It's trying to pull it down, and in fact it will. In a split second the ball will start to fall. So that sometimes can be a trick question, as what is the acceleration at the peak? It's still the acceleration of gravity. The other unique thing in this situation is there's a symmetry involved that you can take advantage of. Say I pick a point here on the left. At that point the ball is traveling at, say, 10 meters per second. And of course that's on its way up. Well, at the exact same position or y position on the way down, now that the ball is going down, but at that same point it's also at 10 meters per second, only now if you think about it in the negative direction, it is now falling at 10 meters per second. So there is a symmetry involved here, because when you toss the ball, as soon as it leaves your hand, the only thing acting on that ball is going to be gravity. And so the gravity that is slowing that 10 meters per second down to 0 to reach the peak is the exact same gravity that now is going to be pulling the ball and speeding it up on the way down. And so since it's the same force acting on the way up, only in the opposite direction on the way down, you're going to end up at the exact same speed on the other side at that same height. So that's a shortcut you can use sometimes on these problems. The third thing I wanted to mention that sometimes to better understand the problem, sometimes it helps to split the problem in two. And I find that sometimes it makes more sense in my head, even though the equations apply across the whole range here. Sometimes it just helps me to solve a problem as the ball going up. So let's say time. If they want to know the overall time from tossing up to when it comes back down to the beginning, you could just use the equations, put everything in, and you can solve the problem beginning and ending. But occasionally, to make myself make more logic in my head, I'll calculate it to the peak here. And so I can do the problem solving it to the peak where your velocity goes to zero, calculate the time to do that, and then realizing that it takes that same amount of time to come back down here to your hand again. And so the overall time would be 2 times that first t that you calculated. I just find when I work with students, sometimes that just helps them understand what's going on a little bit better when you use these equations. So you may find that as a way to help you better understand it. Thank you.